Hey, dog. Hey, dog.
All right. So let's kind of review a little bit where we've been so far with atomic theory and where we're going. So just a little quick, in a nutshell, review. What did Democritus?
We learned about this on Friday.
The idea, right?
Did we learn about this on Friday? No. We have, this is when we took notes in the lab.
Okay, this was the idea that the atoms existed, right? This was around 400 BC. You really didn't have any technology at that point. But he opposed the more popular philosophies of Plato and Aristotle. Plato and Aristotle thought matter was continuous, that you'd never reach a point where you couldn't break it down. Democritus had a different idea. Actually, where the term atom came from. But he thought that we'd get to a point in any matter where you couldn't break it down any further. And what real world analogy can we use for his model that he was thinking? Yes.
Legos.
Legos, right?
Lego my Lego.
So, because he thought that atoms were all different shapes and sizes, and they stuck together to make other things like Legos. Now, of course, he didn't call them Legos. They weren't around before. Legos been around for a while. That's our real world analogy. All right, then who put some evidence behind this thought?
John Dalton.
Right.
I'm going to do that. Okay, well, shut up. She just wrote something. Yeah.
So we listed all the parts of his theory. I'm not going to list them all again. But he came up with the first atomic theory, right? Where he actually put evidence behind it. And he pretty much used other people's experiments and kind of gathered it all the data together and put it together. He used a lot of the experiments that were dealing with the law of conservation of matter, law of definite proportion, definite composition, and law of multiple proportions. Those were all part of his theory. Basically, that everything's composed of these small particles called atoms. These atoms rearrange themselves in chemical reactions to form new compounds. They come together in simple ratios to form compounds. But he did think that all atoms in the same element were identical, and atoms of different elements were not the same. What do we know today, though? We didn't talk about that, but you guys are probably familiar with them. Like all atoms of the same element, are they identical? Like all atoms of gold and all atoms of sodium, are they identical in every way, in mass, and everything? What has been discovered since then that we'll talk about soon?
I know, but I know that. I know it's like that. Okay,
Not all gold atoms are exactly the same. They all have the same number of protons. There's something different about them that we didn't know about at this time because we didn't know about protons and electrons. Yeah. Well, he added that. So that was not part of his original theory, and he did add that because at first he thought that atoms could only come together in one ratio, like carbon and oxygen. But then we realized, oh, we have carbon monoxide and we have carbon dioxide, so they can come together in different ratios. But when they do, they're completely different. And we'll get to it. But did you ever hear of isotopes?
yes.
Okay.
Yeah,
So isotopes are atoms of the same element that have different numbers of neutrons, which gives them different masses. But he couldn't possibly have known that yet because we didn't even know if there was anything smaller than that. So he came up with the first atomic theory. What was his?
Model.
Oh,
The billiard ball.
right. And what date about was this?
Oh, 1808.
And like I said, I'm not gonna ask you what a test. I'm not gonna ask you the dates and all that, but it's just to kind of put it in perspective of when things were occurring and how much more quickly things were discovered as time went on. So his was the billiard ball. basically the atom is the smallest piece of matter that exists, like a billiard ball. They just stick together and form compounds. They're different sizes. All right. Then who came along? Who came along after?
Let me check. JJ.
Right.
Thomson.
JJ from Outer Banks. That was him, actually.
So J.J. Thomson, I think it's Joe.
This is like
Joe
John.
Joshua.
Joseph
Joe
John Thomson.
Joseph John. Yeah.
He just went by J.J. with his friends. So.
Yeah.
J.J. Thomson.
Yeah, and we're his friends. Yeah, y'all.
And who else kind of worked or gave
Oh,
furthering information?
Robert Miller.
Robert Miller? He's not a principal's name?
OMG.
Robert Millikan. Robert Miller.
Villain?
All right. So what did they give us information about?
Electrons. Electrons, and then he found, what did he find out? He found the charge to mass ratio.
Right. So J.J. Thomson is the one that actually detected electrons, right?
Yeah.
He's the one that actually discovered that they existed and came up with the
Would you consider these people geniuses?
charge to mass ratio.
That was a
Okay.
genuine
And then
question.
he found, and then Robert found the magnitude of the
Why
charge
did
of
you have-
an electron, and then determined its mass.
Right.
Using the JJ ratio. Yeah, I just said that.
Yes.
Would you consider these people geniuses for figuring this out?
Yeah, I mean, they definitely knew what kind of experiments to set up.
How do they know? That's
What were J.J. Thomson's experiments?
J.J. Thomson, he did the cathode ray tube.
Catherine.
So he found his information out using cathode ray tubes. What did Millikan use? Okay. And what years did this all take place?
At 1897.
All right, so J.J. Thomson around 1897, Millikan around 1909. Okay. Just to go to the time period. So we went 2,200 years from having the idea that the atom existed to actually having evidence that it existed. And now we're starting to find things in much shorter period of time. This is going to keep getting smaller and smaller and smaller, the distance between the years. So 2,200 years, then almost 100 years, right? Now we're just going to start seeing things, find information out over and over. What was his model, J.J. Thomson's model? Yep.
Chocolate chip cookie.
Right. It's officially, it was called the plum pudding model, but we could visualize it better as chocolate cookie dough, right? Because he was saying, okay, we have this big, there has to be something positive holding the electrons in, right? Or they wouldn't just stay in the atom. So he's saying we have this big positive mass, and the electrons are just distributed through that mass. So we could visualize chocolate chip cookie dough a lot better than plum pudding. I don't think.
I didn't even know that was a thing.
I don't know if it's still a popular dish in England or if it was just in that time.
Did you ever eat it?
I did not ever eat plum pudding. But it's basically just plum flavored pudding with raisins. That sounds delicious.
Oh my god, I have to stop that. Man. Sorry.
I'd rather eat rice pudding. with raisins.
Yes,
Yes,
rice pudding.
Love rice pudding.
I got. What do we? It was like
Did I
rice
ask
pudding.
All right.
No, but-
So let's take a little break and watch there's little short video segments on their experiments just to kind of get a better visual. I know I drew really great pictures of these, but
Yeah, I like your picture.
let me share my screen.
Oh my
Stop
god.
dabbing.
I'm sorry. It's the octopus. It's like ratatouille when we some cook, but it's this. It's the
That's actually fun.
Is that your dad's hat?
Yeah,
Yeah.
and his shirt.
I thought it was.
Stop.
They're really fun.
I will, no, I had to smell test it.
Ow!
It was fine. It doesn't smell like anything. He said he hasn't worn it in years. I was gonna wear his work glasses, but then,
Shut up.
well, I can't take it off. I can't take it off because
Your dad needs to cut his hair.
he said he's gonna buzz it. And I'm gonna die.
My dad wants to grow a mullet.
Your dad is nuts.
All right, I'm not sure.
It would be cool.
No, it would not.
But he's going on that same team next year.
I'm not ruining.
Okay.
If he breaks his coach's heart,
his coach's dog.
So-
yeah.
Here is JJ Thompson.
This is not serious.
I do not. I do, they're back here.
Hold on, I gotta be my No, I'm gonna be Brian.
All right, so we're gonna watch a video here on JJ Thompson, and then I'm gonna switch over to Millikan.
What about John Dalton?
I don't have a video on John Dalton. Oh, yeah, I have this one.
What kind? What kind?
Wild legs there.
Well, it's the strawberry or apple. Who all wants one?
Let me make sure my
your
sound
hand.
works here.
A cathode ray tube is the four.
Cassie, shut up.
I'm not, I am recording.
I don't, someone says like cartoon like.
I can eat a
All
broken
right,
one.
so this moves along really quickly and just gives a lot of information in a really dry way, but it helps you visualize. So this is a cathode ray tube. It looks a little different than the one I drew on the board, but cathode ray tubes can take different shapes depending on what you're doing. In this case, he was looking at the charge going through a tube and the different gases glowing different colors and that type of thing. So you'll have to pay attention as they're going. I may pause it real quick at a couple places.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate-bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Okay, so there's his ratio, okay? So you can see that that's a pretty large number, right? If you're looking at the charge per gram of electrons. So you'd have to move that decimal place 8 places to the right. Okay, so you'd have to add 6 zeros on there. And that's how many coulombs per gram that electron gives off. So it's giving off a lot of charge for its size, right? That's per 1 gram of electrons, which is a lot of electrons. We're not going to worry about that equation that they were talking about. Just looking at getting an idea of how large this charge is for its size. Oh, that was the end. I'm sorry.
A cathode ray tube is the forerunner.
All right, now I want to
A
switch
cathode
over.
ray tube is the forerunner of the television.
Just trying to get it to the beginning. Now I want to switch over to a different tab. So here is Millikan. So are we ready for Millikan's oil drop experiment?
Yep.
I'm so ready.
Good.
She's so ready.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron.
So if you look, that's an extremely small mass, right? So an electron, you'd have to move that decimal 28 places to the left. So you'd have to put 27 zeros on there, then 910, the mass of an electron. Okay. So the masses that are listed up on the periodic table, they don't go out enough decimal places to even take into consideration mass of electrons. Okay, so the protons and the neutrons are much more massive than the electrons. The electron mass is almost negligible, but it packs a big charge. Okay, it has a lot of charge for its size. Okay. Questions on that?
The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
So now we can go back to.
Yeah. Wait, what were you
Yeah. Wait, what is that? Are you working?
All right. So back to
Let's calculate how many.
our progression. Oops.
Oh my God, great.
All right, so let's take a look now at what's coming next. So now that we know electrons exist, right, and that there has to be something positively charged holding them in, now scientists are wondering what is this positive mass? Or what's this positive stuff that's holding the electrons in place? So the next person we're going to talk about then is Rutherford.
I've heard of him before.
She has heard of him before.
He's done lots of stuff. This is just one little.
I have had 79 drinks.
I think he's from New Zealand.
Me, to the private game.
Okay, so far we're looking at English scientists, Dalton, Thomson, and Millikan.
Is he French?
Ernest Rutherford is from New Zealand.
No,
Ew.
it's Spanish. He's in.
I love New Zealand.
And
The accent.
remember when you were doing the atomic target practice, the rolling the marbles under the cardboard?
Yes, definitely.
Okay, that was
Mr. Ernest.
kind of trying to copy his experiment. That definitely has some limitations, but it kind of gave the idea of sending something through and hitting something, right, to try to determine the composition of the atom. So when you did that experiment, you were really looking at one gold atom individually, okay, which is almost impossible, right? When he was doing his experiment, he was using gold foil. So he had lots and lots of gold atoms, although he used a really, really thin piece of gold foil. The reason he picked gold is because gold is super malleable. You can roll it really, 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 really thin without it tearing apart. That's why if you ever looked at old, like ancient or antique Bibles, some of them have like a gold lace pages around the outside because you can really get gold nice and thin and then like plated kind of on the pages there. Now I'm sure that they look like gold, but it's not actually gold.
She.
Okay. But what he's known for is
My church.
he discovered the atomic nucleus,
I love her song.
and what his experiment was
Quit hubbling.
his experiment was the gold foil experiment. Showing the gold foil. So the way he set this up is he took a piece of gold foil.
Why don't you say?
Okay, so you had thin gold foil, right?
Why can't it be big gold foil?
Because you need to be able to.
Yeah, he needed to roll it out as thin as possible. He wanted to get it as close to an atom thickness as possible. Wanted to get it as close to an atom thickness, which is impossible, but he wanted it as thin as possible.
You wanted to be able to create.
All right, he surrounded the gold foil with a fluorescent screen. Because he's going to aim nuclear particles at this, nuclear radiation. And when nuclear radiation hits a fluorescent screen, it lights up. So that's how he was going to be able to detect where the radioactive particles were hitting the fluorescent screen. Now, when you did your experiment, that was kind of like when you traced the path of it going under the cardboard. That was kind of like the detection of where the alpha particles, which were particles, were hitting. Okay, so we also had out here an alpha source, which just means it's some kind of mineral that gives off alpha particles. I think you probably use uranium, radon, or something like those things. But does everybody know what an alpha particle is? Have you ever heard of alpha particles?
Big dog.
Big one.
They are the largest of the three most common radioactive particles, actually.
Radioactive.
They're positively charged.
Whoa, whoa, whoa.
Alpha, beta, sigma, alpha, beta. Yeah, that's awesome.
Like,
What's that thing called?
All right, so this is the alpha symbol, right? They're positively charged because what an alpha particle is, an alpha particle is actually 2 protons and 2 neutrons. Right? An alpha particle is 2 protons. It's composed of 2 protons and 2 neutrons. Right? Has no electrons, but it's basically equivalent to a helium nucleus. Okay, so it's not helium because it has no electrons. Helium has electrons. But it's what a helium nucleus would look like. That's equivalent to an alpha. All right. So these alpha particles were aimed right at the gold foil, right? And what he observed is most of them went right through. Okay, so most hit the fluorescent screen right behind the gold foil. Most of these particles went straight through the gold foil. Some of them reflected. And a few actually came almost straight back. So what did that tell him about the atom? Well, the nuclei are definitely really tough. Okay. The fact that most went straight through meant that they weren't hitting anything positively charged or coming even close to something positively charged.
So that means they're positive? Wait, wait. Yeah, the negative and positive attract each other, so if it's the same thing, but they go.
Right. So there had to be a lot of space in the atom because most of them are going right through without being deflected at all. But you're right, the ones that were deflected, since they're positively charged, they had to come close to something that was
Positive.
positively charged. Right?
Wait.
If they were being deflected away,
No, but he
okay,
said,
pushed away.
he made it tricky. He confused you, I mean. He confused, because he was like, well, if they're attracted to something, that means blah, blah, blah.
Well, if they'd be attracted to something, they'd be attracted to something negatively charged.
Yeah,
right?
but
It's
you
opposite
said
attraction.
if they were attracted, if they went near something, wouldn't, you are being silly.
If
you
they
were
went
just-
near something that was the same charge, then it'd be deflected, right? Repelled. So the fact that some were deflected and bounced back,
Okay, twin. I mean, shut up and.
there is something for you. So these alpha particles that were deflected or bounced back were coming close to something that was positively charged, right? But though it had to be really small regions because most of them weren't deflected, right? Most of them went right through.
Yeah, pretty much.
So what that told him is that there's small, dense, positively charged regions, which would be the atomic nucleus.
Year
So
now.
whatever was deflecting these things away, it was really tiny, but it had a lot of charge packed in a small place, right? Because the way he described this, where it would bounce straight back at the source, he said that would be like taking a huge bullet, shooting it at a tissue, and the bullet bounced right off the tissue. That's how much force was back. So that was the nucleus. All right, so we'll take a little pause there if you want to take a break. Okay, so this all was taking place around 1911. And he was working with other scientists, Marsden and Geiger. You may have heard of a Geiger. Ever heard of a Geiger?
No.
All a Geiger counter is, it's a machine you use to measure radioactivity. So it like keeps every kind of radioactive particle. Now we're exposed to radioactive particles all the time. Sun, there's just natural background radiation because minerals and different things give off radiation. If you eat a banana, there's some radioactive acid from the different isotopes. Some isotopes are radioactive, some isotopes aren't. So there is a small amount of radioactivity that's given off from a banana and other things. So we're always exposed to radioactivity. You use a Geiger counter to measure that. It's when you get above background radiation that it's harmful. So like when 3 Mile Island happened, there were people around 3 Mile Island using Geiger counters to see if there was any contact reaction occurred. So those were the people who just went on Geiger and Marsden, coming up with these different ideas. Now he knew that the nucleus was extremely tiny compared to like the rest of the atom. Since most of the particles got through this little foil without even being deflected, you knew that there was lots of space between these regions, these dense positive charged regions. Does that make sense? So when you are thinking about the atom, okay, you have all the protons packed into this little tiny space. Now there's no name for this model. I don't really know what name it is, but his model, you have this really tiny nucleus where all the protons are packed together. The gold is number 79, I believe. So there's 79 protons packed together in the nucleus, okay, along with neutrons. So they're all packed together in this tiny space. And then around this nucleus is where all the electrons are hanging. But remember, electrons are extremely small, right? They're much, much, much smaller than even protons. So this space out here is 100,000, not 100,000, 100,000. 100,000 times larger than nucleus. 100,000 times larger than nucleus. So that's a lot of space around. That's supposed to be a J. Let me just rewrite that. I'll just write that. 100,000 times larger. So if you want to kind of get a visual, a little bit of a visual, but it's still not as massive as what this electron cloud would be. But imagine going out to the football field and I put a dime on the 50-yard line. That represents the nucleus, that dime. Then I give you guys like BBs. You have to throw the BBs at the nucleus from the bleachers or outside on the track around the football field. How many times do you think your BBs are going to hit that dime? Probably not very often, right? So that represents all these alpha particles that aren't hitting anywhere near the nucleus, right? Every once in a while, you might get lucky and come close to the dime, right? That represents the ones that are deflected. And if you're really lucky, every once in a while, one might almost hit head on, right? Hit that dime. You'd have to throw a lot of BBs to get one to hit it. So that's kind of like what his experiment was. So most of those BBs you're throwing at the dime on the right line aren't going to make it anywhere close to that dime. So it tells you how much space there is around. In order to really get the amount of space, you have to get 100,000 times larger. Any questions on that? Okay. So I also have a video on Rutherford that I want to show before we move on to the lab. Let me pause this again real quick. My screen. So then we'll share. I think we're good to go. All right. So what you've all been waiting for, the video on Ernest Rutherford.
But it wasn't that long ago that scientists knew very little about these basic
We'll
units
start
of
it over
matter. Microscopes and similar technology, we can see.
There.
Thanks to electron microscopes and similar technology, we can see individual atoms. But it wasn't that long ago that scientists knew very little about these basic units of matter. Ernest Rutherford carried out several ingenious experiments in the early 20th century that helped create nuclear science and move forward into the modern age. Rutherford grew up in New Zealand. He was so smart, Gandalf himself sent him to Cambridge University to do research after college. Actually, Rutherford just got a real-world scholarship, but he was really smart. He went to work for a scientist named J.J. Thomson, who later won a Nobel Prize for discovering the electron. Thomson had a theory about atoms called the plum pudding model, but just hang on to that idea for now. We'll come back to it. Rutherford liked to take on the gnarliest problems in physics, and he devised experiments to learn more about radiation. He discovered and named its 3 different types: alpha, beta, and gamma. Rutherford was a top-tier experimentalist. He worked with alpha radiation for 9 years before he had enough useful data to declare its particles were positively charged. Rutherford had a hunch that these alpha particles were a form of helium atoms, but he needed more proof. We'll come back to that, and also the plum pudding, I promise. A better understanding of radiation led Rutherford to discover nuclear decay. When an element like, say, thorium produces radiation, it can become a whole new element. Since radiation is particles escaping from the nucleus, if the number of protons in that nucleus change, then the product is a new element. Rutherford now wanted to use radiation to learn more about atoms themselves. So he moved back to England, this time to the University of Manchester. There, he started working with a young researcher named Hans Geiger. Yes, the same one the counter is named after. Fun fact, the counter actually came about from an experiment that Rutherford invented. Anyway, by 1908, Rutherford was able to prove that alpha particles produce the same light spectrum as helium. See, light spectra are like fingerprints for the elements, so alpha particles and helium matched, confirming his hypothesis. That same year, Rutherford won a Nobel Prize for his work in radiation. But of course, he wasn't done. He set Geiger and a younger student named Ernest Marsden to work with an alpha particle again. His group designed an experiment where they launched alpha particles at a thin piece of gold foil. A circular screen around the setup would show a glowing point where alpha particles struck it. The alpha particles seemed to pass right through the gold foil, striking the screen on the opposite side. But Rutherford had a hunch. He told Marsden and Geiger to keep an eye out for alpha particles hitting other parts of the screen. Sure enough, they soon observed a few particles that were apparently bouncing backwards off the foil. Rutherford's recollection of the discovery is famous. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you, he said. The gold foil experiment led Rutherford to his own model of the atom, one that effectively launched modern nuclear science. And now we talk plum pudding. Rutherford's mentor, J.J. Thomson, described an atom that was mostly positively charged with some negative bits scattered throughout, much like raisins in a plum pudding. Appetizing, right? Instead, Rutherford envisioned an atom that was mostly empty space, with a positive charge concentrated just in the nucleus and electrons orbiting around it. Most of the positive alpha particles simply passed through, but when they struck that nucleus, the positive charges repelled each other. That action sent some of the particles bouncing back towards their source. This is what makes Rutherford a great experimentalist. He let questions, curiosity, and intuition guide his experiments, and then he built a theory when he had enough rigorous proof to support it. But like plum pudding leftovers, Rutherford's atomic model was short-lived. In 1912, a student named Niels Bohr joined his lab. Bohr himself would soon elucidate the structure of atoms, including discrete orbitals where electrons tend to exist. The Bohr model overthrew Rutherford's and lives on with minor adjustments to this day. For Rutherford is remembered for the experiments that kicked off atomic science and as a mentor to some of the greatest chemists and physicists of the 20th century.
Okay. So that just gives you a little bit more background on. Any questions on that? And Niels Bohr, who they mentioned at the end of that video, just happens to be, we'll talk about more tomorrow, the next scientist that we're going to look at as far as the model. So what Bohr is going to do is he's going to say, well, how are the electrons moving around in all this empty space? Because all Rutherford said is, here's a nucleus and out in the space are the electrons. But he had no way of describing how those electrons were staying there. Because people were actually skeptical of, even though it had proof, people were skeptical that these electrons would just stay out here. Because why wouldn't they just be attracted to the nucleus and stick in there, and we'd be back to the plum pudding, right? So what's keeping these electrons out there? That's where Bohr comes into play. And then the more modern time. So let me stop my video.